Hello and welcome to TidyX, a screencast where we go through and try to explain how code works. All right, this is going to be episode 10, and we're really excited to get going here. My name's Ellis Hughes. I'm a statistical programmer at Fred Hutch Cancer Research Center.
And my name is Patrick Ward, and I do data analysis in sport, and you can always hit the both of us up at tidy.explained@gmail.com.
All right, so the data set this week is volcano eruptions. It comes from the Smithsonian Institution. It looked like this week there were a lot of great submissions, but this week Patrick and I actually decided to do something a little bit different than what we normally do. So we wanted to go through and kind of explain a little bit of the process of exploring the data set, because normally we just go in and start explaining how somebody has already visualized it. So they've already gone through and already done the explorations. But we thought it might be fun for us to maybe take you through how we might start when we get a new data set, exploring it and seeing how it works. So we've put together a little script here, and we'll step through it now. Patrick, you want to start us off?
Yeah, so we'll check this out. It's probably an important one given the topic and where we live. There at any point we could be wiped out by a volcano.
Yeah, got Rainiers in our backyard, so
exactly.
be careful of those lahars.
Exactly. So all the usual stuff, kind of to start out, we load the packages that we're going to be using today. We'll obviously always load Tidyverse, which gives us the suite of packages that we need for data cleaning and visualization, and then Plotly for a little bit of interactive data.
Mm-hmm.
And we set our theme there so that we don't get the kind of the stock gray theme from ggplot.
Yeah.
And we'll load in our data using Ellis's Tidy Tuesday R package there. So everything coming from 512. I think there were 4 data sets, of which we'll use 3 of them.
Yeah, I think there were 5.
Five.
So we, I think we've covered this before, but just to quickly highlight these 2 lines here. These will then suppress all the warning messages and just package startup messages. So Tidyverse, I think most people are aware, has a lot of messages, very verbose when it starts up. And so if you're trying to knit a markdown document, if you wrap it with these 2 lines here, it won't print out to your markdown document as you're trying to run it. So just a quick highlight of that.
Yep.
All right. So we downloaded the data.
We loaded our pack. We loaded the data in. We've got the volcano data. We've got the eruptions data, and we've got the events data, of which we only need a few of the columns there that are necessary. And same thing with the volcano data. So we actually create a little subset called volcano info, which gives us some of the meat and potatoes. In particular, we wanted things like country, region, and then the population that is residing within 100 kilometers of the eruption site. All right, so we'll do a little bit of data cleaning here. We're going to only work with confirmed eruptions. There's a few different eruption types. You'll see that in our exploratory data analysis. And then I just kind of went back up here to our cleaning step and threw that in. So we only looked at confirmed eruptions. And then we join in our data of eruptions with the volcano info. And anywhere that there is not a start year, we just filtered that out. And you'll see why here at the next step. Ellis created a measure that basically tells us how long or how many days in length the volcano is erupting for. So why don't you take them through that kind of cleanup procedure there?
For sure. So the data set that we got had everything split out into year, month, and day, if they had that sort of information. So I think every record, because we filtered by ISNA, had a start year. Not all of them had an end year, but that's okay. That just turns this into an NA value. But then there were cases where like end month or end day had the value of 0. So I would just replace that to be the January, so 01, or the first of the month. And so this line here generates a string for each row that looks like year, so the 4-digit year, then the 2-digit month, so like 01 for January, 12 for December, for example, and then the day of that month if it had it, and it separates them with that dash there. So it ends up looking like 2020, 05, today's the 17th. So that's the format that we end up with for each row. And so then we can throw it into as date, which will convert it into a date object, which then allows us to do date conversions and date manipulations here, which is what we then do in this step here. So diff time is a function that's in base R. You put in the end time that you care about, the start time that you care about, and go, okay, what is the difference between these two guys here? And then you can specify units. So it will automatically try to determine what the best unit is to be using, but that does it on an individual basis, so it can get a little bit confusing. So I like to define the units that I want it to be using, and most of the time it's days. I believe there are like seconds or a few other options there.
You can do it.
Yeah, seconds, minutes, hours, days, weeks.
Yeah.
I find days to be the most. Usually I'm working on a day scale. Weeks doesn't really add much information to me. I can quickly get to that from days if I want to. And then seconds and minutes and hours, those, most of the time when I'm working on stuff, that's not really helpful to me, but just know that those are options. And then auto means that it'll try to select the best one out of these. But if you want to make sure that your data type stays consistent, define it.
Yeah, you could, because they're seen as dates, you could actually just do end date minus start date. But with the diff time, you can specify the units there. So we use days. Actually, I use seconds a lot. If you're dealing with, in sport, like player tracking data, and you're looking at velocities and like instantaneous velocity, like second to second changes, we'll actually use diff time with seconds quite frequently.
You're dealing with a different time scale, I think.
Yeah, exactly. Yeah.
All right, so let's execute all that.
Run that. And now that we have kind of our data cleaned up like we want, we also join in just a few of the information about the events of the volcano. So we'll go ahead and do that. And we don't specify any by in the join. We let R identify that it's going to join on volcano number, volcano name, and eruption number, and retain the extra columns in events.
Yep.
So we then jump into a little bit of exploratory data analysis. For the first one, it's just how many, counting the number of volcanoes per country within the data set. And then we just retain the top 10 here to kind of keep it simple. So we can look at that.
All right.
Oops.
I ran that, so I ran over there. Count, that's a function that'll allow you to just pass by a single field that you want to be counting across. So this kind of has to be a categorical variable. This sort true means that it'll reorder everything. Top 10 will then look at that and figure out, I need to be organizing by the N. I think we've covered this fairly frequently, but we define the aesthetics right here. Because country it'll be converted into a factor automatically. Here, you're telling it to respect the order that you put it in.
Correct, yeah. Reorder it by N.
Yeah. So
N being the count. Yeah. And so then we get that plot that you see over there on the right. And maybe surprised to see that United States leads the charge with the number of different volcanoes that are erupting or have erupted over the years within this data set. That's confirmed eruptions, of course.
Yeah.
When you dig a little bit deeper into this, there's a lot that take place in Alaska. So a lot of the eruptions a lot of the different volcanoes are in Alaska, and then some out in Hawaii and things like that. So not necessarily all of them are what we think of as the continental United States, I suppose.
No. Yeah, and I was surprised when I saw the U.S. at the very top there. I knew Japan would probably be pretty high, Russia. Yeah. I mean, those just logically made sense, but I was just surprised with the United States there.
All the countries in South America, Mexico, those are. Iceland has had a big one in I think it was 2020 actually. I think it was
2020. This year?
Sorry, 2010.
Yeah.
Yeah.
Okay.
We also look at the distribution of intensity. So volcano intensity is measured on this VEI scale, which is a log scale, and it's a scale that ranges from 0 to 8, and it defines the amount of I think it's like the amount and distance of like the discharge of volcanic ash. Isn't that what it was?
Yeah. We were
Volcanic
curious.
lava.
We wanted to bring this up. The Tidy Tuesday link told us to go to this website here. They kind of explain, okay, this is VEI 0 through VEI 8. This is why like context about what you're analyzing is really important. Because we're like, oh, 6. So what is that? Like, why weren't there any 8s when we were doing?
8 means death.
Yeah, basically
colossal.
eight means that things aren't going good and people are dying.
Yeah, there was a few 7s. They didn't end up in our final data set because we were only going with confirmed and had to have a start date. But one of the 7s, the few 7s that were in this data set, was actually very close to where we live in Crater Lake. And I can't remember the year on it, but it was
like negative 5,000 or something.
It was like negative
that.
5,000, exactly.
So 5,000 BCE. So yeah, it's interesting to see the seismological background of this area here, because
whoever was living in Seattle back then, it was a bad day, bad.
Not a good day.
Yeah, exactly. So we'll plot a histogram to start, just kind of giving us a look at the types of eruptions. I expanded the limits of the x-axis to go all the way to 8. Even though there's not an 8 in the data set, as we just discussed, I did think if we're representing the data and the scale appropriately, it was important to include it there and at least just show that there was nothing.
Yeah, and so it looks like there's a number of 2s, which is, I was also, like, when we were talking about this earlier, a little bit surprised that the number of 2s, because, I mean, you hear a lot about, like, Hawaii or those places having a lot of really, really minor eruptions, and so I would expect those to be like more on the 1 scale. And it sounded like when we looked at the VEI like Wikipedia page that those were kind of that, but apparently there's a lot of 2s in the world there.
Yeah. We also then just made a nice little table of the eruption VEIs. They're using the quantile, so we can take a look at, there's 25 to 75 will represent our interquartile range. The 2 there is the median value. And then the max value, like I said, was 7. We haven't seen any 8s in there, thankfully. And then 0 is obviously down at the bottom there, the minimum value. And then we can also plot, so I took the top 5 countries and I wanted to plot these not the quantiles, but the distribution of the eruptions on VEI that we've seen for these top 5 countries. So I did it with a few different ways. One that I've used here that we haven't used before is from the ggforce package. This function called GenomeSina, and you'll see what it does, but it's basically like doing a jitter plot of points, with the exception that it also extends the data horizontally when there's greater density. So there we can see, for example, Chile, Indonesia, Japan have very large amounts of density around the 2 range VEI eruptions. Russia slightly smaller, and then United States slightly smaller than that. But Russia, you could see a larger horizontal width for 3s, for eruptions that are in the 3 range. So if you remember the count plot, United States is at the top, but you can see that many of the eruptions have not been substantial in terms of their intensity. So you can see, I mean, we lead the charge with 0 eruptions there. So, that's probably eruptions taking place in Atlanta, in Alaska, out in Hawaii, places where they these things are just sort of erupting, but they're not really affecting anything because they're not too intense.
And then Atlanta? Come on.
Yeah, not in Atlanta. I overlaid a violin plot on this. Violin plots are just nice ways of looking at data. Basically, what they are is sort of like if you were to plot, we've plotted joy plots before, which are kind of like just histograms by category, or density plots by category. And if we plot a violin plot, it's basically like a density plot with a mirror of itself. So it creates this sort of nice looking shape there.
So you can see how it works across the various things, and you can kind of compare across the multiple. Because then, if you don't have the same equal amount of records for each, for Chile versus Indonesia, you can look at the densities to go, look, they're more likely to have a 2 here, but they're both pretty highly compared to the rest of the distribution to have a 2.
Yeah.
Like,
Yeah.
kind of allows you to look across multiple axes.
Yep.
It can be a bit to take in all at once, though.
Yeah.
All right.
All right. So that's
and then you did some additional.
just added, the typical niceness stuff and
Yeah.
made it look pretty.
I think I ran all that.
Yeah.
Yeah.
So there you
caption, things like that. Make it look pretty. It's very important.
Then the types of eruption categories, again, we only stuck with the confirmed eruptions, but there you can see there was a lot of uncertain eruptions, and then there was some discredited eruptions. I don't know exactly what. Is that like some kid and he calls in to like the earthquake center and says, I see something going on, and then they discredit him? Or, I don't know exactly.
No. It wasn't that. It wasn't.
I don't exactly know what that means. But.
Well, we can look to see. I don't think they really describe here.
No. Yeah.
Because it would have been category, right?
Type
of eruption. So apparently they thought it was an eruption, and it turned out not to be.
It wasn't. Yeah, it was a false alarm.
Yeah, which is good. I mean, I guess less eruptions.
Yeah. Also, then, what years do we have confirmed eruptions for? So, since we're dealing with only confirmed eruptions, just to get a sense for how the data is dispersed across time.
Mm-hmm. So once again, you do a count on start year, take the top 10, tell it to respect your ordering with that.
Yep.
Fairly standard, defining the coloring of the column plot there, define your title.
Yep.
Just want to make sure that we're covering these things too, just to make sure people understand what's going on. We're explaining everything, right?
Yep. There we go.
Right. So yeah, it's interesting the order. Because this isn't in time series order. This is
number correct.
Of eruptions.
The next one will be in time series order. This is just in number options. 2010 was an interesting one. Like I said, when we look at a time series of this over time, 2010 is like for some reason had an absurd number, even compared to like the past 200 years.
Yeah.
An absurd number of eruptions. I don't know what that was all about. I can't recall really what happened in 2010. But it wasn't that long ago.
No.
We'll do the same thing looking at just the 2000s. So here we filter on the start year over 2000. Same type of count. And this is in here. We're not going to order it by the. So you'll notice in the aesthetic, I don't maintain a reorder there. Because basically what I want to do is look at this as a time series. So as Ellis said on the last plot, if we run this one, now we'll see starting at 2020 at the top and 2000 at the bottom. Obviously 2020 is very low because we're only 5 months in to the year. So we haven't racked up everything that we can possibly rack up so far. But
and everyone's been staying at home, right, for the last 3 months or so.
Right. So. Yeah. So not a lot of action, right?
No.
There you can see 2010 was kind of large. 2004 had a lot, and 2000 had a lot. Since 2010, you could see that it's kind of been like a downward trend. We've kind of trickled off a little bit.
At least in confirmed.
At least in confirmed eruptions, correct. So don't know really what that's all about, but interesting, I suppose.
Mm-hmm.
And the next one is the intensity of the earthquakes on a VEI scale. So the number of VEI eruptions, again, going since 2000, so greater or equal to the year 2000.
And then also removing any cases where VEI was not defined.
Yeah, whenever it didn't get defined.
That wasn't helpful.
For whatever reason. So there's just, again, stuff that we already kind of have figured out. 2 seems to be the most typical VEI amount, or VEI intensity.
Yep.
We haven't seen any 8s. We haven't seen even any 6s in the past 20 years, which is again probably a very good thing.
Good thing for us, safety.
Yeah.
Yeah.
Although I guess what's dangerous is if you do look at that VEI scale on Wikipedia, it tells you the typical frequency that you would expect an intensity. So if we haven't had one in 20 years and it looks like 6, so we only went back 2000. If we went back to the 1980s and maybe we don't see any of those sixes, we might be due, which
Yeah,
also,
that might not be good right now either. I mean, they
yeah,
keep on telling us. I mean, Patrick and I both live in the Seattle area. That they keep on telling us, the big one's going to happen. The big one's going to happen. Mount
yeah.
Rainier, St. Helens, big earthquake. They keep
Water
on telling us
volcano.
that's going to happen. Well, hasn't happened yet, thankfully. But
Yeah,
we're always a little bit anxious and prepared.
always do. Yeah.
Yeah. All right.
Uh, we'll get into a little. ggplotly is just a super like user friendly way to use. We've used Plotly a little bit in previous TidyX's in order to kind of show you how you can create some interactive graphics. ggplotly is like an even easier way to do this, where literally you build your ggplot just like you normally would, and then you wrap it in this ggplotly function, and it gives you a cool interactive graph. So, Ellis, why don't you go ahead and
Sure
go
thing.
through this one?
Sure thing. All right, so we take dat, which is defined earlier to have all this information there for us. We're gonna filter to only keep volcanoes that were in the United States, just to decrease the amount of information that we have to go through and process. And then also we limited to the start year to be 1950 or sooner. So part of this was, once again, limiting the amount of data that we had in there, but also part of it was the fact that we're going to be using this population with 100 kilometers value here, and that isn't done by a year. So that I don't know when the actual recording was done for what is the population within 100 kilometers, but I don't imagine if we were to be looking at like 1550 that would be the same as if we were looking at 2010. So I thought I'd just limit the amount of data or amount of years that we're looking back. So hopefully it's still relatively accurate. It's not going to be super accurate. Next, we're going to group by volcano and eruption number. So this is just so that there were cases where eruptions were listed multiple times. And so I wanted to decrease the number of times that it was listed, get the start year that it happens, what type of event it was. So I believe this would be the confirmed records there, get the VEI of that eruption, get the length of that eruption, and get what the population was around that volcano at that time. We ungroup because we grouped by multiple values here, and summarize after you run that will only drop this last record here. They're looking at changing the behavior in the next release of Depplier. Then we're going to remove any cases where we don't actually know the eruption duration. Here I am going to be generating a label that doesn't show up inside of our ggplot, but as soon as we throw it into Plotly, this becomes important. So we're going to be using some HTML tags around there. So BR stands for break. So it'll kick it off to a new line. This will make more sense in a second. Then we're going to throw it into our ggplot. We're going to set the aesthetic, so the X, the Y of, so the X-axis is our start year, the Y-axis is how long did that eruption last. The size, which is going to then be used by genome point, is how large the dot that it draws is based on the population within 100 kilometers. We're going to color it based on the VEI, and we're going to set the label, which shows up down here, which we defined right here, to be volcano. I'm going to actually log scale the y-axis because durations could be really long. Like most of them were relatively short, within like 10 to like 1,000 days, which I mean 1,000 days is still pretty long for an eruption, but some of them were like 10,000 days. So at that scale, it's kind of hard to see everything. So if you take this log scale, it squashes everything down and then highlights. It still allows you to highlight the ones that had a long duration, but it makes it easier to then to see the lower durations. Set the labels to be year and eruption duration. So let's quickly run that, and let's just quickly show what it looks like in normal ggplot.
There you go.
So there you go. You got everything here. You see the various. This is all the same. These 3 or 4 big dots there are all the same volcano. She had already looked at all this.
Yeah.
But I don't know. It's just interesting to see the way that it all kind of played out. Everything.
Because this is a static graph, your tooltip that you set in your aesthetic, where you said to label, it doesn't show up. That's a key thing. So when you're going to use this ggplot function, if you were to just run that function without setting a label, as Ellis did in his ggplot2 there, aesthetic, if you didn't set that, when you run ggplotly, it's just going to give you an interactive plot where as you roll over the points, it just tells you whatever you specified on your X and Y axis. So the kicker there is that exactly by setting the label, you get this cool tooltip that you can roll over and see. So there's St. Helens. The other big one is St. Helens, St. Helens.
Kilauea. Yeah. So we defined how this label should look like with the Volcanoes record there. And so the BR made sure that we then went down to a new line for start year, category, duration. So you have all this information within the tooltip.
There it is.
And that's a nice thing. And then with Plotly, we can zoom in like, what happened here? Kanaga.
Kanaga.
Yeah. We
erupted
probably...
What was that? 325 straight days.
Yeah. Some of them were erupting for a pretty long time. St. Helens, 1990 was for 101 days. So I don't know. It's just a fun way, and also you can kind of then quickly with the tooltips here, kind of go over look to see if there's patterns. Like Kilauea shows up a lot when you're just quickly going through this.
Yep.
So I thought it was kind of fun. Kilauea.
It's active, but it's not threatening anybody at the moment, I guess.
Exactly. Just low level of eruptions.
Yeah,
so.
which is often like what they say, isn't it? Like they'll say, this volcano is an active volcano, and you think of it as like what you might see on National Geographic, where there's lava spilling out everywhere and rolling down the side of the mountain and creating all this havoc. But in reality, just because it's an active volcano doesn't mean that it's necessarily negatively impacting anyone, or these things are just kind of like going on under the surface, and we tend to only hear about or get what gets reported is the big catastrophes, but
the big ones.
Yeah.
All right. Well, I think that was everything.
Yeah, that's Volcanoes.
Yeah.
There you go.
Well, thank you all for coming and listening to us. Once again, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward, and you can find me on Twitter at OSPPatrick. And you can reach the both of us in Gmail at tidy.explained@gmail.com.
All right, thank you, and keep exploring your world.